So first of all, I would like to say that it's my great pleasure and honor to be here. It's really, it's a one-time during the life achievement in the career that I had. Now here, I remember when I was a PhD student, second year PhD student, first time that I attended RILEM committee meetings, and I was pleased in sitting in the RILEM committee meetings with all the important professors and next to them and talk with them, and I never thought really that I could be here one day and presenting for you. So thanks RILEM, thanks the committee who selected me. It's really a pleasure for me. And I think this medal also has a clear message for the young researchers who are at the beginning of their career, that if you work hard, if you are persistent enough, and if you are consistent enough, and maybe if you dream big enough, you can achieve and you will be acknowledged. So thank you very much. So today I'm going to talk a little bit about mechanics and durability of textile reinforced composites, a topic that I started when I started as a postdoctoral researcher at the University of Minho. I think it's not necessary to give another brief review of where I've been or what I've done. So thank you for Professor Bell that introduced me. So I'm going to skip that part if you don't mind and go directly to the talk. So we know we all aware of the two big and important challenges of the construction sector today. One of them is the deteriorating infrastructure and built environment that we have, and we need innovative and effective strengthening conservation strategies for those structures so that we can extend their life and we can ensure their safety. We also have new structures and growing construction development, especially in developing countries. And for both of these problems, both of these challenges, we need new materials, we need efficient materials, we need new materials, and we need sustainable materials. And considering the recent sustainability, durability, and resilience considerations, we need to be sure that these materials that we are using are cheap, are sustainable, are durable, and are available locally and globally. So this is actually, I think, one of the biggest challenges of the construction sector at the moment. And for that, happily, we have several new opportunities. We have several new materials. We have alkali-activated materials. There are a lot of RILEM committees on this topic also, and on their durability. We have blended cements. We have fiber-reinforced concretes. We have textile-reinforced mortars. So we have a lot of options at hand at the moment, but all of them share some challenges, and the challenges of those are that the variability of the properties of these materials, all of them have a wide range of variability in properties, so it makes them difficult, it makes it difficult to control the durability and quality. Also, there is a lack of understanding of durability of all these materials. So that's the reason that there are a lot of RILEM committees and also a lot of articles and publications on these subjects during the last years. So if I want to talk a little bit about textile reinforced mortars, which I personally worked on it and used it for a strengthening of masonry structures, but these materials also are applicable as new for construction of new structural elements, such as light shell elements, right? So it's not only limited to strengthening applications. So what are textile reinforced mortars? We have a similar thing in fiber reinforced concrete, but fiber reinforced concrete, the difference with textile reinforced mortar is that fiber reinforced concrete is consisting of short fibers. Textile reinforced mortars are usually long fiber grids embedded in an inorganic matrix that make the final composite material, which we call it textile reinforced mortar or fiber reinforced cementitious matrix, also it's called in the literature. So we have a wide range of textile types and variations. We have glasses, we have steel, we have basalt, we have natural fibers, and they come with all range of configurations. They come as unidirectional, bidirectional, welded, woven, 3D, auxetic. So there's a large range of fibers available in the market at the moment and is being used in practice. Then we have also a large number of matrices. We have cements, we have geopolymers, which are usually used mostly for application to concrete structures, and we have lime and pozzolanic limes and limes with short fibers, which are more interesting for application to strengthening of masonry and historical structures. So as you can imagine, combination of these two leads to a wide range of mechanical properties, durability, and quality, and makes it very difficult to control that really. And if you think about that, we use this for field application, there are more complexities coming at hand, which is the substrate condition, which is the on-site application condition, which is the workmanship, which is the curing conditions. So all these can affect the performance of these materials. And we don't know if we apply them today, are they going to work as we want or as we expect or not? So the question I ask myself, and we ask ourselves before when we started this research, it was that can we control or predict the performance of these systems in service? Can we control and can we somehow understand how all these parameters can affect the performance of these strengthening system during the service life of the structure? To answer that, we have to also pay attention that this is a highly complex and multi-scale problem. If you look at the structural application, we have the mechanical response of textile reinforced mortar and its bond with the substrate that control the behavior of the strengthened system. And if you go a scale below that, we have the mechanical properties of the fiber and mortar and the interaction between them that control the behavior at upper scale. And then if you go a little bit inside that, we have the chemistry of the binder and the fiber and the interaction between them, transport properties of the binder that control the mechanical response, and finally the durability as well. So if you want to have a clear understanding of how these materials work in practice, we need to really understand all these scales and how they are linked to each other. And then we have also the effect of processing method, the effect of curing method, and the effect of environmental conditions, that each of them can have effects on some of these scales and globally affecting the performance of the final structure that we have. So if you go to the literature, we see a quite large number of studies on this topic, on the mechanical characterization of textile reinforced mortars and their application to masonry structures. I think the most notable one is the experimental results of the RILEM TC250 CSM that I also had the honor to be involved in and work on that. The rest of the studies, as I said, mainly cover the larger scale testing and the mechanical characterization and the structural characterization test. Well, because we are structural engineers, right, so we only care about what is the tensile strength, what is the fracture properties of our material, and then if it's working well in practice or not. So there is really a lack of standard also testing methodologies at a smaller scale for these materials. There is a lack of studies that combine all these scales together to clearly understand how the behavior is affecting. There is a lack of material structure property links in these systems. And also there is really a lack of durability studies on these systems. I know there has been a very few recent studies on this topic, but we still need to do a lot of more research. The available studies are really, really few at the moment. So what we have been trying to do was actually to cover this gap and try to somehow connect all these scales together. So in the last 5 years, we have been focused on the upper rectangle, the gray one, and we have been trying to connect the fiber and to mortar properties to the structural performance in the field. And then now currently we are trying to connect that to the chemistry of the material at local scale. So I was thinking how to organize this research and give a brief overview of what I've been doing, and I thought maybe the best way is to divide it in 3 phases. So the first phase was that really working on developing consistent testing methodology so that we can test these materials from the material level to the structural level, and then use these testing methodologies to extract the constitutive laws that are applicable in numerical simulations, then validate and develop computational tools that are able to predict the response of these systems at the structural scale, validate them with laboratory small scale testing, and then use that tool for predictions. So this was the first stage that I'm going to give a very brief overview of that. So we have developed several test setups at different levels. So material testing is very standard. That doesn't need any development. But we have developed several test setups for fiber to mortar pull-out characterization. Then we have developed our own tension stiffening test setup for tensile characterization of textile reinforced mortars, and then we developed our test setups for evaluating the bond between textile reinforced mortar and the substrate, and then also to go to the structural scale and performing the structural scale application. So somehow we have been trying to connect all the scales in a consistent way to make sure that the loads are applied in a consistent way in all the scales of the testing. And then we have tested, once we had these test setups, we evaluated the performance of a wide range of textile reinforced mortars, different fibers and types of mortars, also different fiber configuration, unidirectional fibers, bidirectional fibers. So we investigated how these combinations of fiber mortar types can affect the performance at the local level and at the structural level. For example, I'm showing here some results of pull-out tests showing that how effective bond length, for example, in glass fibers embedded in pozzolanic lime can change, or how the transverse fibers in bidirectional fibers can change the pull-out response significantly. So these observations should be considered in the constitutive laws that we are developing later on, right? So having a wide range of testing on different combinations of fibers and mortars, we developed constitutive laws for the pull-out response of the fiber to mortar behavior, and then we use that for upscaling to the tensor response, and then validating it with experimental tests, and then using those information as the input of computational model that can predict the response of structural elements strengthened with these materials. And then our predictions were not only at the single building level, but we also went a little bit larger and at the more global scale. And today we can predict the response of masonry facades, large facades strengthened with these composites. So in summary, what I tried to show you that how we went from the fiber to mortar bond behavior and mortar properties to the structural performance. This was the first stage of the studies we did. In the next stage, we tried, and that is a continuous process at the moment, we are trying to understand the role of all those parameters that I talked about in the beginning on this whole range of behavior. So how mortar age or curing, or how environmental conditions can affect the performance of these systems really through all the scales. So as an example, we investigated the role of curing. If we cure the mortar in a dry environment, or in a short wet environment, or in a prolonged wet environment, which is very sensitive in real applications, because in real applications you cannot really control the curing conditions. So what happens if you are applying this material in a dry day or in a wet day, and how that affects the performance at the structural level is important. Or for environmental conditions, we are investigating the freeze-thaw behavior, alkali environment, high temperatures, or even carbonation effects on the performance of these systems through all the scales. So just to show you an example, I'm showing here the pull-out response of steel fibers embedded in mortar, and it shows that the curing condition can significantly affect the pull-out response of the fiber, and that consequently affects the bond slip laws that can affect the tension stiffening of the strengthening system, and then the performance of the whole structure at service, let's say. Or the mortar age can have a significant influence on the pull-out response. And that shows that maybe the 28 days testing procedure that we have been following from cementitious studies might not be really applicable to these materials and to these pozzolanic limes, let's say. So maybe we need to find new standard and new testing methodologies for these materials. And then at the moment we are trying to couple these results with material science experimental testing so that we can better explain the reasons for these changes that we observe. So just a short overview of what we have been seeing. We have been seeing that curing conditions, processing and substrate conditions can have a critical effect at various scales on the performance of these composite materials. And microcracking and deterioration of the interface between the fiber and mortar are the most common deterioration mechanisms that can happen because of these issues and also under different environmental conditions. So this we know. At the moment we are trying to develop computational tools that can also simulate these deterioration mechanisms and coupling it with the previous computational models that we have so that we can, so that we can somehow optimize the repair design of these systems at the beginning in the design office, let's say, considering the properties of the materials, the environmental conditions, and the application procedure that is going to be used. In the future, we are also trying to see if we can use some on-site indicators so that we can online monitor the curing conditions and the properties of the material so that we can, in an online manner, we can update the design of the system so that we can take care if we see if something is going wrong during the application or if the conditions are not appropriate enough, we can, let's say, update our design strategy and application. So at the end, I would like to thank everybody. Thank you for listening to me. Of course, this work was not only my work, was the work and was the result of several collaborations, the help of several students, doctoral researchers, several friends, technicians, and everybody who have supported me. Sorry, I didn't put any names because I'm afraid to forget the names, but it's a very, very long list of people who supported me. So I would like to thank all of them for supporting me until now. Thanks very much.